Welcome back. So in today's lesson, we're continuing exploring the sky, and we're going to introduce to you several gentlemen, the early astronomers that helped our modern way of thinking about astronomy. Let's see if I can get back to the beginning here. So this is chapter 3, and our what are we summary that I always like to kind of start out with. The summary that they talk about in here is we are thinkers, and so we are intelligent and we can think about nature and the universe, so it ends up making us very special in that we can think about the universe that we are very much a part of. We are the part of the universe that can think about nature and understand just what are we. Okay, it's kind of the theme that this book, Astro, takes us through. So the origin of modern astronomy is chapter 3. Like I mentioned, there's going to be some interesting gentlemen, the early astronomers. We do want to first kind of back way up and think about the early kind of Greek philosophy on astronomy, their idea, astronomy before the gentleman we call Copernicus. He was our revolutionary figure that really helped pull us from a paradigm, sort of a set way of thinking that we were stuck in. And so we introduced Aristotle, the brilliant philosopher, as they call him, and really later a follower of Aristotle's principles, which are these principles that you just don't question them. Things are just how he described them, just because that's how it is. This idea that the heavens, heavenly bodies were perfect and unchanging. And then the closer in that you got into Earth, it was more like hell. The center of Earth was hell. And so there's this box, this paradigm that we were in, these first principles, these things that you just didn't question. So yeah, our first gentleman, Claudius Ptolemy, comes from that line of these Aristotle's principles. And also remembering that the solar system, a galaxy, and the universe, so they thought of the universe as the solar system at this time. This idea of a galaxy wasn't even thought of during this time. So that's something to think about. But those first principles deduce some truth about the universe by reasoning with these first principles. So no need to think them any further, so just accept it kind of a thing, which is not scientific thinking, what we call scientific thinking now. So Aristotle's universe, the ancient kind of universe, heavenly objects move on circular paths at constant speeds. So perfectly circular, all right, in uniform speed. The speeds didn't change, so that's something we've got to think about. And Earth is motionless at the center of all of this. So an Earth-centered or geocentric is what they call that. Ptolemy's idea of how Earth worked. Okay. Something as you're viewing from Earth, the planets seem to follow some rather complicated pathways. Every now and then it looks like they'll be going along one direction and then hover for a while, and then after several days they're starting to trek in the opposite direction. We call that retrograde motion. Okay, so their observations of the planets, they're trying to fit a model that would explain retrograde motion. This backwards kind of motion is difficult to explain in terms of constant speed and these perfectly circular motions they were finding. So Ptolemy, Claudius Ptolemy, our gentleman, P is silent, so Ptolemy, had this idea that Earth is centered at the center, motionless, and that you have the sun and the other planets, okay, going in these little epicycles, he called them, and little difference. So they go like this, and then they have the little loop-de-loops, these epicycles, and it got pretty complicated. But his was the geocentric model. Okay, this Earth-centered, geocentric model of the universe. Okay, let's see. So, mathematician Claudius Ptolemy, and so he was interested. They actually were interested in the motion of the planets to kind of help with the calendar, and so yes, they all have their papers that they were writing, and so that was sort of Claudius Ptolemy's idea. Then comes along Nicholas Copernicus. He's our revolutionary fellow. So 1473, Nicholas Copernicus. Let's see, Nicholas, how does he spell that? Let's see. Some of them have an H in there. He comes along and he decides in his model he's going to put the sun at the center. Again, they're interested in trying to get the lineup and the matching of the position of the planets over time. And Ptolemy had to keep adding those little loop-de-loop-de-loops to try to get things to match the actual observations. So Copernicus comes along and he puts the sun at the center, so the heliocentric. Is the Copernican model, they call that. So he moves the sun, so you know, the Earth just becomes an ordinary planet like all the other ones. So this idea of Earth being the center of the universe, that we were the center of the universe and everything revolved around us in the Ptolemy model, well, it wasn't matching up what the observations were. And so he thought outside of the box. He really changed the paradigm within which we think about the universe and the motion of the planets. And so heliocentric, putting the sun at the center and having Earth just be one of the other planets that orbits the sun. Okay, so now here we got motion for the Earth. It actually is moving in this Copernican view. Copernicus also stuck with the uniform circular motion of the orbits of the planets, so he did keep that, and he kept that they were at the same speed in their orbits. So this did present a little bit of a problem with keeping up with the positions over time, okay? But it really explained the retrograde motion quite nicely. So yes, the heliocentric model, okay, was Copernicus's kind of idea. And you've got to keep in mind that the Catholic Church was in charge with this, and they believed in the geocentric model. And so here comes a little renegade here throwing everything out of balance, and it didn't go over too well. And so this De Revolution Orbium Celestium was the book that Copernicus wrote, and he was very hesitant to publish this, but you know, he got encouraged, and he finally did send it in 1542, and then died in 1543 before it even got printed. But that hesitancy to go against what the church taught was a major concern, because people were burned at the stake and tortured for going against what the church believed in. And so right away, he could explain this retrograde motion, very straightforward. He didn't have to have all the loop-de-looped epicycles that Ptolemy had, very complex. And in science, you'll find that the most elegant and simple explanation is your best explanation. So here he was, where imagining like a racetrack is always kind of what I think of on this. You got the sun in the middle, all the other planets going around. Well, it will look like, if they're all kind of going around in their circular motion, every now and then one of the planets, say one of the runners, will pass, okay, another planet. And so from the perspective of Earth, right, another planet will seem like it's going along same direction, and then all of a sudden it starts going the opposite direction because it's overtaken us, passed us by in the orbit. And so that really does nicely explain the retrograde motion. Okay, and so retrograde motion is exhibited for those planets beyond the Earth. So not Mercury and Venus, but Mars, Jupiter, Saturn, and so on down the line. So it really explained retrograde motion in a snap when we finally put the sun at the center. So yeah, apparent. So as it's kind of taking over and passing by, it looks like, you know, it's going the opposite direction, but it's just our viewpoint from here on Earth. And that makes really good sense if you have all the planets, including Earth, orbiting the sun. And so that was sort of a nice contribution that Copernicus gave us. But now, in keeping up with the position of the planets, over time, it did have a little trouble. And the reason is that he stuck with the perfectly circular orbits. They're not really perfect circles. They're very nearly circles, but they're a little bit elongated, okay, or ellipses. But he stuck with that circular motion and uniform motion, constant speeds. Well, the planets really don't stay the same speed throughout their orbit. There are times they're moving a little faster and times that they're moving a little slower. And so because he stuck with that uniform circular motion, he couldn't keep up with the positions of the planets very well, or really any better than the Ptolemaic model. Okay, but this idea of placing the sun at the center, that part of his hypothesis was spot on, so that was good. Okay, but yeah, keeping that circular and a uniform circular motion was an issue. Okay, so the simplicity of the idea is what is important. Let's see, I think that's the, yeah, a little bit more on that. We can continue though. So the next person to come along and contribute is Tycho Brahe. And he's a gentleman on the left there, and he has a prosthetic nose that said he lost his nose in a duel or something like that. But very wealthy nobleman who built this incredible observatory. So at this time, you got to think, there were no telescopes. So telescopes had not been invented yet, and but he had all these sights and peepholes and things where he could observe the motions of the planets, the locations of the planet, and he kept very precise and detailed naked eye observations, like 20 years of naked eye observations that were so precise. That's more or less his contribution to astronomy. And then this gentleman on the right, Kepler, Johann Kepler, is a gentleman. He was a poor mathematician, not wealthy at all, but a poor mathematician that was extremely sophisticated with a talent in mathematics. And he was really able to get these three laws of Kepler's, the motion of the planets, to really help us understand the motion of the planets. And so let's just take a look at some of these. the Danish nobleman, Tycho Brahe, um, in 1572, so they call this new star, is actually a supernova, but they named it after Tycho's supernova, new star. It's really a supernova, which is an explosive, cataclysmic, explosive of a star, death, okay, which we'll, in our star unit, talk about the deaths of stars, but a supernova. Very bright, okay, and Tycho Brahe was trying to calculate the parallax for this. So remember, parallax is that apparent motion of an object really due to the observer position changing. And so this new object, bright in the sky, Tycho's supernova, new star they called it, he was trying to calculate the parallax of that little angle. And he couldn't calculate one. And so it turns out it was just so small of an angle that, you know, we didn't have the sophistication of being able to detect that small of an angle yet. So he came to the realization that this star, new star, was actually much, much further out, totally away from the Earth. And this caused a problem because the heavens were unchanging. Remember the Aristotelian view that the heavens were unchanging. And so how could that possibly be farther away from Earth? Because the closer you got to Earth, the more imperfect things were. So that there could be something changing, like a new star all of a sudden. But because it was so far away, they're like, well, how can that be? The heavens are unchanging. And it really was because that was such a small angle that he was unable to get the parallax, that little angle on it, the new star. So, you know, he was thinking, how could that be? So it got him to thinking a little bit that maybe some of these first principles, Aristotelian first principles, weren't on target, really. But really, for 20 years, Tycho measured the positions of the stars and the planets with such great detail that it was a phenomenal thing that he was able to do. Soon, though, he hired Kepler. He hired Kepler, that very talented mathematician, to help him out with some calculations and things. So here comes Tycho, and it was, here comes Kepler, and that not long after he hired Kepler, that Tycho passed away. And so here is Kepler, the newcomer, that now has inherited these 20 years of very precise observations. Okay, and he ended up replacing Tycho, okay, this newcomer, but of course at a much lower salary because he was not nobility. And so this is our story of Kepler, and Kepler gave us 3 laws of motion. He just empirically observed the planets' positions, and he worked out the mathematics of it for us, so really was able to give us a book. Of course, they all kind of wrote some books trying to understand the orbits of the planets. And from those observations, okay, he had finally solved the mystery of why they had to kind of keep tweaking those positions of the planets. It really wasn't keeping up with their models. Now, Kepler favored the heliocentric model, the Copernican model of the universe, which was really the solar system. So he had the sun at the center and the planets orbiting around it. But what he went away from was he found from his sophisticated mathematics that Copernicus used the uniform circular motion, right? So perfect circles and constant speeds. Johann Kepler figured out that they are not perfect circles They are ellipses, very nearly circular. So for him to be able to see that those were ellipses was phenomenal. Very talented there. And he abandoned the circular motion and the constant speeds. Okay, so he had variations in speeds as the planets got closer to the sun versus farther away from the sun. They changed their orbital speeds, and so of course he had a couple books in there providing this information. So that key to that solution was that these were ellipses. And so when he changed that up, he was able to keep up with the changing positions of the planets over time. So it really simplified things for us. So Kepler definitely has contributed. 3 laws of motion. They of the planets, of course, motion of the planets. And so the idea of ellipses. Okay, so here we have something that is a little oblate. So it's not perfectly circular, a little oblate in there. So you have 2 foci, little thumbtacks, got a string here, okay, and then you can draw ellipses in this manner. And so we've got some terms in there that sort of define an ellipse, okay, the geometry of an ellipse. One's called the semi-major axis, abbreviated with a little a in the calculations for these. And we won't be calculating any of that. Well, not an ellipse anyway. Some things, and I'll write the equation for that and let you know. But it's half of the longest diameter. So here's the diameter of the ellipse, and it's half, okay, of that longest diameter. So half of it is called the semi-major axis, okay. And the eccentricity, there's a little calculation for that. Again, we're not going to be calculating these, but it's half the distance between the foci divided by the semi-major axis. So let me back up one. So half the distance between the foci, okay, divided by the semi-major axis, okay? So a little calculation you do, and you can get that number will either be close to 0 or close to 1. The closer that number is to 0, the more circular, perfect circle your ellipse is, okay? The closer that gets to 1, the more oblate, elongated that ellipse becomes, okay? So yeah, nearly 1, very elongated, close to 0, more circular. So depending on just how far apart your foci are, you can get either a more perfect circle or a more elongated ellipse, okay, with that. So a little relationship that he was able to come up with. Finally realizing that these weren't perfectly circular orbits, they were ellipses, okay? The magic bullet there is that they're ellipses, not uniform circles, okay? Okay, the second law of planetary motion that Kepler helped us with was the speed of the planets does change. It's not uniform speed, constant speed, that the speed changes, okay? So the amount of time that it gets swept out here from A prime to AB, so we're closer, A prime to B prime. The sun, okay, is closer, okay, sweeping over equal areas though, okay? This is the same equal area, but farther away, going from A to B, okay? The sun would move, or the planet would move faster, okay? Fastest when it was closest to the planet, and then as it went in its elliptical orbit, which is really exaggerated here, it slowed down, okay? So it traveled fastest when it was closest to the sun. planet should travel at its greatest speed when it is closest to the sun. Okay. And so that was another thing that really helped cinch this heliocentric model and the position of those planets that they were observing, those precise observations. He really was able to explain it better than anyone had up to this point. And so another thing is his third law is that two quantities, the orbital period and the semi-major axis, are related in a nice little relationship. So the period of a planet, which is the number of years that it takes to make one complete revolution or orbit around the sun, is represented in an equation. So this is really his third, Kepler's third law. The other two we had in the PowerPoints there. But so the little relationship here, P2 equals A cubed, and that's in years, so I'm going to put a Y down here. And as long as the semi-major axis, A here, okay, is in astronomical units, we have this little relationship that we can do between the orbital period, okay, and the distance from the sun. The semi-major axis is this relationship here. So we could calculate if we could observe and see and determine how many years it took, so the orbital period of a planet, we could calculate how far away from the sun that planet is with this relationship. Johann Kepler helped us with this, figuring out the distances of the planets from the sun. That's amazing, because all he had to do was observe the planets, for a year and figure out, how long it took for it to make a complete revolution around the sun. So phenomenal relationship here. They do give us an example of, let's see, the one that they have here is Jupiter. I'm going to probably do a different one here, but the average distance from the sun, okay, which is the semi-major axis, so the A, is 5.2 AU. So we had, in this case, we had this entity, okay, the semi-major axis. Well, okay, you're going to cube that number. That number gets cubed, the semi-major axis does. So what is the period then? Okay, so that number cubed gives us 140.6 right there. So take the square root of that. Square root of that, and that'll give you your years. And so 11.8 years is the period, okay, for Mars to make it all the way around the sun. That's his orbital period, okay, in years though. That's this relationship. Let me do one for Mars here. Let's say Mars is 1.52 AU. So this is for Mars. Just to give you another example. AU from the sun. So that's its semi-major axis. Okay. And we want to know what the orbital period is. So Mars's orbital period. Well, basically, you're going to set that up like this. So P squared equals A cubed. Okay, so we're going to take the 1.52 and cube it, okay, which is going to give us 3.51. I hope you can see this low on the board. Okay. But that's the orbital period squared. So we do have to take the square root of, okay, 3.51. Okay, and that's going to give us P, okay, not P squared, square root of, and that's going to end up giving us 1.87 years as the orbital period of Mars. And so that's this idea that it was amazing that you could observe the orbital periods, because that's something that you can observe, their location over time, and figure out the distance, and vice versa. You know the distance, you can figure out the orbital periods. And so Johann Kepler was very influential in helping us with the mathematics with his 3 laws of motion, and he solved a huge mystery because he was able to tell us something about the motion of the planets. Now this was all empirical, meaning strictly observations of the planets. He didn't know why they went in these elliptical orbits, you know, that he had no clue as to why they were doing what they were doing. All he was observing was the observations, the positions of the planets, okay? And then working out some very interesting mathematics. So it's describing a phenomenon without knowing why it actually occurred. We're going to see that it took Sir Isaac Newton to help us out as to why the planets were going in the orbit around the sun. So, but those laws are what we call then empirical, that they're strictly from observations. And so this is key to scientific theory or scientific thinking, which wasn't, you know, commonplace in ancient astronomy. And so there's a little levels kind of confidence. How do we know? I think it's on page 48 in your book, where it kind of talks about the scientific method and that sort of thing, where it distinguishes a few terms. One is a hypothesis, and so a hypothesis is just a single kind of conjecture or idea on something. So that's kind of our first step in science, is to come up very creatively, come up with an idea on something, and really it must be tested. Something that can be tested and must be tested. That's a hypothesis. Next, we talk about a scientific theory. Now, these have been tested, experimentally tested, and widely proven. So time and time again, many people have repeated it, and that that's been proven to be true. And so those are known as scientific theories. You can one-up a scientific theory by what we call a scientific law, like the law of motion, planetary motion that Kepler gave us. These have been tested in every inconceivable manner, and they have been proven to be true and are widely accepted. The law of gravity that we'll be talking about, Newton gave us those. But yeah, these are just starting now to think in a scientific manner, where empirical observations, you're just making the observations, okay? You're not trying to make up, you know, any loop-de-loops and try to make it fit what you think is going on. He strictly went by what he observed, and then from that was able to come up with some mathematical relationships. And it's incredible what he helped us to understand on the planetary motion. That's Kepler's law of motion and contribution to modern way of thinking about astronomy. Our next gentleman, Galileo. Galileo Galilei, Italian, right? And he, along the way, had adopted the Copernican model, and he really thought, yeah, he's on to something. That seemed like the conceivable, model. It made sense to him. But again, he was very cautious about it, as many of them were, because you did not want to go against the church, and the church supported the Ptolemaic model, this geocentric model. So again, Galileo's time, church in control, and you don't want to go against that. You could be burned at the stake, tortured. He did end up being imprisoned, but you could understand kind of the cautious nature that they would have, because people were put to death for this. But Galileo did not invent the telescope. Okay, that was something that a lot of people think. He did not, but he was the first to use the telescope and turn it to the skies and make astronomical observations. He was the first to do that. The Dutch lens makers were the first to make the first telescopes, and then Galileo kind of got the specs from that, and then he made his own model of that to turn to the heavens and make his observations. But so he did not invent the telescope, but he was the first to turn the telescope and make observations of the night sky and the planets and such. So, he wrote some books as well. Some people were quite apprehensive to look through the telescope. They thought maybe this was witchcraft, that they couldn't believe what they were actually seeing. So, of the time, so it's kind of strange. But he would wrote some small books and things. Maybe not a whole lot in them on everything, but in these, some of his telescopic observations. Kind of putting a kink in that idea, the Aristotelian kind of first principles, that the heavens were perfect and unchanging. Well, when he turned his telescope to the moon was not perfect. The moon, he found, it looked kind of like the Earth. I mean, it had mountain ranges and these deep valleys and craters in it, and so the moon was not perfect. And so that was starting to put a kink in these first principles of the heavens. Well, the moon was out there with the heavens, so why did it look so much like the Earth, which was closer to hell in that Aristotelian kind of viewpoint there. So it was not only like Earth, I mean, it was imperfect, it was even an Earth-like kind of a world there. Second thing he noticed when he turned it to look at the planets, he noticed that there were these little, what he called planets. They're actually the satellites or the moons of Jupiter. So he was taking a look at Jupiter, and he saw 4 little planets. They were moons. So these are what we now call the Galilean moons, named for his honor because he was the first to observe them with his little telescope. And it was a rudimentary telescope too, so you can see these with just a very simple telescope. Try it sometime, take a look, and it's incredible to see. You can see the moons actually orbiting the planet Jupiter, even in a simple little telescope. So this kind of puts a kink in the geocentric, in that you could have other centers of motion. It didn't just have to be, here's the Earth in the middle and everything going around. Even a planet itself could have things orbiting around it. So that sort of put in the idea that there could be other centers of motion by observing these little moons, or the Galilean moons, around Jupiter. Okay, so quite interesting to see that. Okay. So the next thing, let's see if he has it on here. He also, surely there was a picture. Here we go. Something else he saw was that Venus had exhibited all 4 phases. So like a crescent and a full illumination on it, and a gibbous kind of becoming a full one. So that Venus went through all of its phases, okay? And that would only make sense if the sun was at the center and the planets, including Venus and Earth, were orbiting around the sun. So the heliocentric model. Venus would exhibit all of the phases, okay? Crescent, gibbous, full, okay? In the Ptolemaic model, it would just have one phase, okay? It would not go through all of those phases, okay? It would have always been like a crescent shape in the Ptolemaic model. Okay, so this is further proof, honestly, of the heliocentric model that Galileo did observe that. So very important observations that Galileo made, empirical observations that he made with a telescope. So he was the first to turn the telescope to the skies and explore the heavens, right? Yeah, so very important in there. So he was a little hesitant, but he was wanting to publish in support of the Copernican model, the heliocentric model. And this did cause sort of an uproar in the church, and he was told not to speak of this, his ideas of the actual heliocentric model, the Copernican model. And, you know, for the most part, he didn't, but he did write a little book, and that he was more or less criticizing those people that believed in the geocentric model. He was calling them very simplistic, you know, minded, simple-minded, and the Pope did not take kindly to that. He was brought before the Inquisition, and, you know, he's like, it moves. I mean, what can I say? It actually moves. But they put him on, you know, home arrest, to where he had to stay at home while he was in an Italian villa. I don't know how bad that would be, really. But about the last 10 years of his life on house arrest kind of thing. But this idea that he had to strike everything out of his manuscript that it pertained to the Copernican model. Lots of censorship going on there. And why? You know, why? Because it went against the teaching of the church, even though he had loads of evidence to support the heliocentric model. So, yeah, there was some issues along the way. Okay. With that, let's see. But yeah, at the end, he was just like, still, it moves, referring to the Earth. It's in an orbit. It's not motionless at the center. So, I mean, he just couldn't not talk about it. Okay. So, yeah, so in his villa for kind of the last 10 years of his life, sentenced to life imprisonment in his villa. I don't know how bad that would have really been. But it was said that he died with cataracts, because he also did a lot of telescopic observations of the sun. You're not even supposed to look at the sun without a telescope, for sure, but with a telescope. So no wonder he did get eye damage to the cornea of his eye from doing telescopic observations of the sun. So yeah, always have the solar protection if you ever observe the sun. So he died in 1642, 99 years after the death of Copernicus. So I always liken these gentlemen as if they're in a race and they're handing off a baton. So they do some exceptional work, and then that work gets handed off to the next person, right? Galileo needs to get put up here somewhere. But Galileo, our next gentleman, hand off the baton to Galileo. And then here comes our next person. So 1642, Galileo dies, and 1642, the Sir Isaac Newton is born that same year. So it's like, let's hand off the baton of Kepler's work and Galileo's work, and then here comes Sir Isaac Newton. So this is just a really nice summary, okay, of these gentlemen. So here's Copernicus, way back here, but it's also kind of giving you other realms, so not just the scientific world, but the art and the literature realm as well. So I really like this summary here. You have this in your book. Here's Tycho Brahe's time frame, okay? Here's Galileo's time frame and Kepler. So they're kind of overlapping one another in the 1600s. Lots of good now dragging us into a modern way of thinking about science in here. This is the revolutionary kind of time period of sort of the rebirth, the reawakening, Renaissance time period. Okay, Shakespeare is in there, Bacon and Rembrandt, so artistic worlds and literature in there. And then, okay, Galileo dies, and here comes Sir Isaac Newton, our next gentleman, okay, with his Principia in 1687. So Isaac Newton's our next gentleman. So they're talking about that Renaissance period, this reawakening sort of period. We had revolutionary kind of time. So Copernican revolution, okay, finally solving the problem of planetary motion, partly solved by Kepler's 3 laws, right? Galileo, right, studied the nature and the motion. He made some important progress on that, but it really took Sir Isaac Newton to finally tell us why the planets were going in their perfect, elliptical motion, why they were going around the sun, okay, in the first place, and why their speeds were kind of varying as they did this. And so Sir Isaac Newton is our next gentleman. Okay, so like I said, he did, Galileo died in 1642, okay, early part of it, and then December 1642, here comes Sir Isaac Newton. And so he really did kind of flower the seeds that were planted of our previous gentleman here. And a few years in there, he was extremely, he got ill and kind of had to stay home kind of thing. And 1665 and 66, he just did a lot of thinking and studying. And he did a lot with optics, which we won't talk a whole lot about here. You could make a whole nother course on the optics that he did. But we'll just focus in on his work with gravity and how that related to the motion of the planets, those forces acting on the planets. And so here are Newton's 3 laws of motion. First one, a body continues at rest or in uniform motion, so a constant speed, in a straight line, unless it's acted on by some force. Okay, so his first law of motion there, an object is going to continue in a straight line at a constant speed unless there's a force acted upon it. Okay, so this sort of helped in the motion of why does the moon orbit the Earth? It should just keep going straight, right? But what keeps it going in a curved orbit? It's almost like it's continuing to kind of fall towards the Earth. This law of gravity, as we're going to see here in a minute. But a body changes of motion is proportional to the force acting on it and is in the direction of the force. So forces kind of come in pairs, equal and opposite kind of forces on there, acting on a body. So the idea that the forces act in pairs, equal but opposite kind of forces in there, in the direction that the force is, you'll get motion. When one body, this will be the third one, when one body exerts a force on a second body, the second body exerts an equal but opposite force back onto the original body. And so we got to think about different masses for these. And so there's a couple terms in here that we distinguish. The masses of an object, the measure of the amount of matter. So depending on what your masses are, you're going to get different amounts of forces. But weight is not the same as mass. So you have the mass, but the force acting on that mass, that's what we call weight. Okay. So an object's weight is the force that Earth's gravity is acting on that mass, okay? That's kind of a distinguish between mass and weight. The measure of the gravitational force on that object is its weight. Okay, and there is a relationship, it's called the inverse square relation. So that this idea of distance between objects become important. So yeah, everything exerts a force on everything else, right? But depending on the mass, right? The greater the mass, the greater the force. The smaller the mass, the less of a force. But also, how far apart are your objects? Okay, so the distance between the objects also is a concern with the force. Okay, so let's just write one little relationship of Newton up here. Okay, between a force. Okay, so this would be Newton's area. Okay, and this is the inverse square. Where F is standing for force and G is the constant for gravity, okay? And M1, M2, so these are two masses, mass 1, mass 2. So the product of your two masses divided by D here is the distance squared, okay? So inverse, so it's 1 over the distance. Meaning that the farther apart, okay, the larger that distance separating your two masses, okay, the smaller the force is going to be, okay. So distance does have an effect on the force of gravity, okay. So this little relationship, not that you're going to do a calculation with that, but sometimes it's nice to see that written out in a mathematical kind of an equation type of form for us here. So that's the inverse square relationship. So gravity is universal, and so Newton's law of motion and gravitation make it understand why and how the moon kind of orbits the Earth and the planets orbit the sun. So they would ordinarily go off in a straight line if it were not a force acting on it, pulling it. And of course, the Earth is very massive in comparison to the moon, and so it's exerting a force and pulling, pretty much just pulling the moon away from a straight line and in a curved motion in an orbit around the Earth. Same way, our sun is very, very massive, okay? And so the planets are small. And so that force of gravity is causing the planets to stay in orbit in a curved motion around the sun, okay? And so, yeah, this important idea about orbiting, okay? It's kind of falling towards the center of gravity. They've got, I don't know, some sort of a cannon that they're shooting a cannonball in this one. But we could also extrapolate that and think about the moon as well. So two objects orbiting each other actually kind of revolve around their center mutual mass here, okay, between the two. This object's clearly larger and this one's smaller. And the larger, more massive object, okay, is going to orbit closer to the center of mass. So you see its orbit closer to the center. And then we got this little one whipping its way, okay, around the larger kind of an orbit there. So center of mass becomes important when we talk about the orbiting of stars. In our star unit, the more massive star is always going to be orbiting closest in to the center of mass. Okay, so noticing the difference between closed and kind of open orbits in there. We don't need to be too concerned about that. But Newton, and finally his universal law of gravity, mutual gravitation. So every object, including me and you, do attract other objects, except we're just so tiny, you know, that we don't have that great of a force. Very massive objects have greater forces. And then of course, what kind of distance do we have between things? The greater the distance, the smaller the force ends up being. So now how gravity can actually explain the tides that we have. Tides, ocean tides are explained by the forces of the moon on the earth and the sun, all three of those exhibiting forces, this mutual kind of attraction kind of thing, creating our tides, okay? And so we talk about a couple types of tides in here. Let me see if they'll talk about them. The spring tides, okay. When you have at two moon phases here, at what we've got here is the, here's the sun, right? The earth, and this is full moon, right? When we're looking out here at the moon, we see the full disk, that's full moon. So this alignment, like this, right in a parallel line, that's full moon, and we see that same alignment at new moon, right? This is new moon. Get that just right. When we look out here from Earth, we don't see the illuminated side. So that's our new moon phase, if you remember that from the last lesson. Again, all lined up perfectly in line. With this geometry, so either new moon or full moon, okay, happens twice a month, right? You're getting an adding together of the attractive force of gravity from the sun and the moon acting on the Earth's ocean, okay? And it's actually pulling out, okay, kind of bulging out, okay, the water, okay? And so that creates higher high tides and lower low tides, okay? With what we call this spring tide. So, you know, twice a month we go through these spring tides. So the extra high and extra low tides, the most extremes of our tides are called the spring tides. The other geometry that we see, and I think they'll show it to us here, is during a first and a third quarter moon. So if we were looking at this, you might not be able to see it too well, right? But our perspective from Earth, the right half of the moon is illuminated, and that's our first quarter moon, right? But also look at the geometry. We are at a right angle, right? There's the sun, the earth, and the moon. So here, the force of the sun and the force of the moon kind of negate one another just a little bit, so that your gravitational pull on the ocean isn't quite as great. We call these neap tides, N-E-A-P tides, okay, neap tides. This will occur at first quarter, and then also you'll see that same sort of arrangement, of course, at what we would call then a third quarter. So if you're looking out from the Earth, you're seeing the left half of the disk illuminated. That's third quarter, right? You remember that? Again, we've got the right angle geometry happening. So at first and third quarter moon phases, we get the sort of partially canceling out the gravitational pull of the sun and the moon, and so we're getting highs and lows. They're kind of leveled out. They're not really extreme like we see with the spring tides, and so the highs are not so high and the lows are not so low, just sort of more mellowed out. And these are called the neap variety of tides. So that's why when hurricanes come around, they are always concerned about what tides we're in. Are we in the spring tides? Because that would make everything worse if you're getting the storm surge at the same time that you're getting your higher high tides, right? Or are we going to be at low tide, lower low tide? So yeah, that's important in meteorology for sure with these tides. But yes, Newton helped us with this gravitational laws of gravitation, and helped us with that force of gravity, and finally the why the planets were going in an orbit, right? Kepler had no idea why the planets were in the positions they were in. No clue. These were just his empirical observations of the planets and the mathematics he worked out with that. Phenomenal. But it took don't forget about Galileo, but it took Newton to finally cinch that what the force was. There was a force that was keeping the planets in their orbit around the sun. So thank you to Sir Isaac Newton for that information. Yeah, and so this is just going a little bit more about that. But yeah, he really gave some good insight on the concept of nature, sort of his general laws, motions of all the bodies under an external kind of forces. This force of gravity was very, very good. But what it made was possible was some predictions. We could make predictions that could then be tested by observation. So this is key to the scientific way of thinking. You need to be able to test it and predict, okay? So predictions are a big part of the realm of science. And so really, yeah, his laws of motion can be used to derive Kepler's third law by using the law of gravity. That was why the planets were behaving the way they were, why they sped up when they were closer to the sun. There's a greater gravitational force than when they were further in that elliptical orbit. They were further away from the sun, so they didn't travel quite as fast. That was, how he was able to kind of derive Kepler's third laws because of the force of gravity on there. So these laws of gravity really helped understand Kepler's laws of motion. So yes, some good gentlemen, early astronomers that brought us into our modern way of thinking about the universe. Okay, but still, the universe was thought to be the solar system at this point. We, really didn't come to the realization that we were even in a galaxy, the Milky Way galaxy, in just maybe 100 years ago. And then even more recent, that there was a universe filled with galaxies. So I think it's always nice to include this little chapter because it gives us a historical perspective of how far we have actually come with the study of the universe. So yeah, that concludes chapter 3. So make sure that as you're going through your study guide that you are able to arrive at each one of those bullets and provide some good information from it. You have the set of PowerPoints. Of course, you have a book, I hope. Hope you purchased the textbook. And then supplement with the videos is great. Or come to class as well so we can get the details of that as well. So that's chapter 3, and we have one more chapter for our unit of exploring the sky. It'll be in chapter 4, where now we're going to start looking at the instrumentation and scientific techniques and tools that we use to explore the sky. And so I will see you next time. Thank you.